Okay, thank you. So my name is Alastair Hodgetts and I'm a PhD student at the University of Birmingham researching the eruptive history of the Mexico City region. Today I'm going to talk about assessing the type and frequency of volcanic hazards affecting Mexico City using a sediment core from Lake Chalco. Or an alternative title could be How to Get the Most Out of Your Sediment Core as a Volcanologist before Chemistry, Chronology and Other Analytical Sciencey Bits. So I'm working as part of the MexiDrill Project, which is based at Lake Chalco on the southeastern edge of Mexico City. Mexico City lies within the Trans-Mexican Volcanic Belt, which is a chain of arc volcanoes which covers the width of the country. As we can see in this Google Maps image, Mexico City is surrounded by a bowl of volcanoes, better seen in this DEM. Probably the most commonly known volcano is Popocatépetl, which is towards the south of the Sierra Nevada volcanic range. Further to the east we have La Malinche volcano, towards the west Toluca, and towards the south of Mexico City, the Sierra Chichen volcanic field, which comprises 220 monogenetic cones. Our core site at Lake Chalco sits directly above this monogenetic field. So the MexiDrill project was completed in 2016 and was drilled consistently for 6 weeks. We can see in some of these photographs from the drilling campaign and some of the cores which were collected. The cores were then transported up to the US, towards Minnesota, where they were split, subsampled and processed. High-resolution images were collected, as well as magnetic susceptibility and other downhole logging techniques. Descriptions were completed and drilling gaps were identified, leading into a composite stratigraphy or splice being produced, this leading on to the scientific questions being able to be addressed. I'm going to talk today about a deviation away from the description into more detailed and descriptive volcanic descriptions, correlations and splice matching, leading to our own volcanic questions being addressed. So a little bit about core recovery. There were 4 holes recovered, A, B, C and D, and we can see in this map on the bottom right hand corner that there was little space between these, less than 100 metres. Lake Chalco is part of the wider sub-basin of Chalco, which is part of the basin of Mexico, which Mexico City lies upon today. We can see that hole C was the deepest hole drilled to over 500 metres depth, and from this figure on the right we can see that consistently around 300 metres we have the lower part of the lacustrine sequence, marked by this high spike in magnetic susceptibility. Below this we have a series of about 100 metres of volcaniclastic material with lavas lying below that. So the volcanics can be split into various different types. Felsic tepers are very prominent throughout the whole core, throughout the whole lacustrine part of that core. Some of them are very thick, up to 70 or 80 centimetres, and some of them are very thin on millimetre scale. Some have lots of texture within them, and some are very fine grained, and some coarser, up to lapillian parts. Mafic tepers have a very similar story. Some are very dark, some have strictures within, some are very thin, and some are very thick. And just this figure here shows that some are in very close succession to each other, with serious cyclic activity between these mafic events. There are other volcaniclastics, the volcaniclastics which are below the lacustrine part of the core, for about 100 metres, looks very similar to this, but also they occur at very small points within the lacustrine part of the core as well. Some of them are very fine grained with high magnetic susceptibility spikes. Some are very coarse grained, polylithologic and quite poorly sorted, and others have clusters of lava, are indurated and even have pumices. The lavas towards the base are mafic. They are vesiculated to dense, and at flow boundaries become very reddened and oxidised. So the splice composite sequence was compiled, and this is where the best sediments which are preserved from each hole are taken, and they're taken jumping between different parallel holes at tie points between these. So for example, in this case we jump from A across to B, back onto A and then to C, and this creates a full single composite splice sequence through the whole of these cores. As we can see on the left, this is a splice. This left-hand column just shows the lacustrine part of the core. On the right-hand side, the full core was the lacustrine into the volcaniclastics and the lavas below. I've defined something called a ghost horizon, which is where tephras or other volcanic layers are not preserved within the splice, but are preserved on other holes which are off splice and do not make it into the splice, are still recorded as a volcanic event, as these are still eruptions that have occurred and we would be missing if just using the splice alone. So the data that I've gathered involved logging all 1,500 metres of core, including some earlier coring projects as well. And this was looking just for macroscopic volcanic layers. So I logged this in a package called SciCat, and I also logged this by hand and also using other techniques as well. Off-splice sections were investigated, as I've said, including these ghost layers, and in total I recorded a total of 29 characteristics about each volcanic layer recorded into a giant database, ranging from age depth data through to grain size, structures, contacts, and my own confidence values in whether the unit is primary or it's reworked, or whether it's even confident it's a volcanic layer. The most useful data was around the deposit type to determine eruptive style, depositional processes. The confidence values allow us to estimate whether minimum and maximum events have occurred. Composition has been ascribed from felsic intermediate to mafic. Grain sizes in phi. Thickness is recorded, as well as event-free depths, and also thickness reliability based on how well preserved that core section is. And here's just a small example of some of the other data that's collected. Some quick stats from the core: we have 649 volcanic layers that occur within that lacustrine upper 300 meters. And if we revise that down to a minimum volume, that's stripping out anything that might be reworked or potentially not a volcanic event, we bring that figure down to 536, which is obviously still quite a large figure. Splitting between that, we can see that the felsic versus mafic output is very similar, pretty much half and half, with a handful of intermediates that are recognised throughout. And the maximum lacustrine core volume that is volcanic is around about 25%, and some other stats there as well. So let's move on to moving this into some plot form. So this is just a plot to kind of show all possible volcanic layers within the core, all possible volcanic tephras that are within the core, as the blue line. As the orange line, anything that we are confident is definitely volcanic, and the grey line, a revised plot which shows confidence of anything that's volcanic and also anything that we think is primary. So really kind of a maximum and minimum of all the tephras. And we can see the same similar trends that come all the way through this, showing that generally there's a decrease in explosive volcanic activity over time. Volcanic output was highest at the onset of the lake, which is towards the base of the core. And there's been a slight increase since around 50 meters, where there was a kind of a lull in activity. We can see that peaks in activity, which we want to investigate further and see where these are from. So we can look at this plot, for example, which splits this out into the same lines as well to show this data. It splits into felsics versus intermediates versus mafics. So we can see generally the felsics do have a depression here, but generally it's a decrease in time. The intermediates are fairly flat line, but the real area where the peaks and the clusters are pulling out is within the mafics. So we can see this here, as we would probably expect if this has potentially come from the Sierra Chichonsi volcanic field and is more related to a volcanic field output. Other plots we can do with this data also show estimated grain size over this long time scale record. This shows the most common grain size in both plots is a medium ash. Thicker deposits generally have a coarser grain size for these outliers in this plot here. And coarser deposits are generally lower within the core, as we can see in this plot here. So there's plenty of plots we can do from this, and plenty of ways that just from this descriptive data we can get some very meaningful volcanological results. So just some take-home points are that long time scale records from contrast settings are unique and can be used to significantly improve our understanding of explosive volcanic eruptions in a given region. Long time scale core records provide a chance to see patterns of volcanism otherwise not observable in the field. Prior to source identification, or a region or city's vulnerability can be assessed over timescales comparable to the lifetime of the surrounding volcano is very important for a place like Mexico City. And outputs of monogenetic fields can also be assessed over timescales much longer than we can recognise by their surface deposits. So thank you very much, and I invite any questions.